Anyway, so in this talk, this is my talk about microservices. And basically, I'm really going to kind of come up with a definition of the microservice architecture and sort of much more precisely define the term, show that it's an architectural style, and actually explain what that means. Because we throw around this term architecture a lot, and it's kind of interesting. We don't really talk about, well, what is this whole architecture thing? So that's actually the first part of my talk. A little bit about me. So I live in San Francisco, so just a short flight away. Well, Oakland to be exact. I got my start in programming back in the mid to late 80s building Lisp systems. So spent like 7 years building compilers, runtimes, everything, including IDEs. And I'm wishing that ever since that Lisp was more popular, really. Wondering why I went to C++ and then Java. 10 years ago, my book, Pojo's in Action, came out. That was all about Spring and Hibernate, which were technologies that were revolutionizing enterprise Java development. And then shortly after that, I started tinkering around with this very obscure service known as Amazon EC2. And remarkably, cloud computing just sort of exploded onto the scene. And along the way, I created a startup called Cloud Foundry that was a path for deploying Java applications on EC2. Upload your WAR file, it provisioned EC2 instances. And then that got acquired by SpringSource back in 2009, right before SpringSource got acquired by VMware. So it was part of that whole, I should say that Cloud Foundry was much more of a plankton than a sort of fish or anything like that. We were tiny. And then, along with Spring and Cloud Foundry, we were actually ejected out of VMware into Pivotal. So I was there for some number of months. But that was a long time ago now. So the past 4 years, I've been pretty much focused on the microservice architecture. Kind of got into it because there was a lot of synergy between PaaS and sort of what now is known as the microservice architecture. Didn't really have a name for it when I first started talking about it. And it kind of solved some problems that we were struggling with when we built Cloud Foundry that was a monolithic application. So anyway, for the past 4 years, been working on, been basically doing consulting and training, working on a startup as well, building an event-driven platform for simplifying the development of transactional business applications. And yes, I'm also working on a book. Shameless plug. I guess I have to get a discount code and tweet it out. You can easily do that because you can get the meat. The first 5 or 6 chapters are out, and as soon as I get them done, more polished, the first 8 chapters are going to be available. Anyway, so that's me. So the agenda for the talk is first kind of quick refresh on software architecture. What the heck is it and why does it matter? Talk about the monolithic architecture, compare and contrast it with the microservice architecture. Talk about a lot of the kind of issues with using microservices. And I'm going to introduce this pattern language that I've been working on that helps address these issues. And I'll talk about applying that. Okay, so let's talk about architecture. So what is it? Because I know everyone likes to be called an architect, right? And because it sounds cool. But what is this? What do we mean by architecture? So this is a classic definition of the term architecture. So it's a set of structures that you need in order to reason about a system. So the goal is to enable you to make some form of decisions about your software system. And it's basically a set of software elements, relations or relationships between them, and the properties of those elements and relations. So that's kind of a lot of words, kind of abstract. You can sort of summarize that down into it. The architecture of a software system is some elements, some relationships, and the properties of each of those. Or, alternatively, you can just think of it as a bunch of boxes and lines. Right, but in reality, that's what architects like to draw. No offense to any architects in the audience, like Sam there. But, it's actually got much deeper meaning than that. So if you think about the structure of this building, It's what are we, 38 floors. So from the architectural perspective, there's many different perspectives on what we mean by the architecture of this building. So if you're a structural engineer, you're concerned with the concrete and steel that kind of defines the sort of the shell of the building, make sure that it doesn't fall down. But if you're an electrician, you're not concerned about concrete and steel. You're concerned about the electrical architecture. Likewise, if you're a plumber, you're concerned about the plumbing. There's mechanical architecture and so on. So there's architecture means different things to different people. And it's sort of multi-dimensional. So that's true for a physical structure like this, but it's also true for a software system as well. And basically, you need to describe the architecture of a system using a set of views, so multiple perspectives. And each view is a set of elements, relations, and their properties. And the classic view model for software architecture is the 4+1 view model. Just out of interest, who here has heard of that? Okay. Yeah, it's kind of this interesting thing that you go back to the 90s maybe, and it was talked when it was, I think, defined. 97 maybe, it was talked about a lot, and then somehow along the way in the past 20 years, I feel like it's faded away. And I remember there was a long time I didn't really think about it, but I was sort of struggling with what is this microservice architecture thing? And then I started going back to this. So that basically defines the architecture of a software system using 4 views: logical, implementation, process, and deployment view, along with the +1, which are the scenarios that animate those views. A scenario shows how the elements within a particular view collaborate, and communicate in order to kind of fulfill a request. So we have the logical view. Since we're programming mostly in object-oriented language, the logical view describes what we as software developers create, which is really classes and packages. And the relationships between them are the relationships between the classes and between the packages. So inheritance, association, aggregation, dependencies, and so on. And then there's the implementation view. That's really the output of the build tools. And that's comprised of modules, which in Java would be jar files, and then also components, which are the executables. So in Java, or deployables. So in Java, jar files or executable jar files or war files. And the relations here are the dependencies between them and kind of composition. So this component is made up of these modules, and this module depends on that module, and so on. And then you have the process view, which are those executable components at runtime. So we go from our classes and packages to jar files and war files, and then the war files are deployed, in this case on Tomcat servers. And the process view would also depict other parts of our system, such as databases and so on. And the relations between them here represent some form of inter-process communication. And that you could have more elaborate properties on those associations to actually show what protocols are used for communication. And then finally, you have the deployment view, which shows how those processes run on, quote, machines or nodes. So those could be virtual machines, those could be containers, and the relations in this view represent some form of networking. And once again, you could add lots of details that would be meaningful to a network engineer. So those are the 4 views, and then you've got the +1, which are the scenarios. So in this example, I've got a sequence diagram that shows how components or from one of those views collaborate in order to handle a request. So from an architectural perspective, you have various scenarios that are of sort of architectural significance, and for each one of those, you would have sort of scenarios that and then describe how the components within each view collaborate. And this, if someone says to you, well, what's your architecture? Well, you describe to them as a document on the whiteboard or in a presentation these views plus the scenarios. It's really, really useful. So that's kind of a definition of architecture and how to describe it. Another really useful concept is that of an architectural style. So once again, if you go back to the physical world, buildings come in various styles, right? Victorian, Georgian, Art Deco, and so on. And the same is true with software architectures as well. And basically, an architectural style constrains the elements and the relationships that you can that are the building blocks of your architecture. This definition, is written by some other people, uses the term components and connectors, but that's equivalent to elements and relations. So it's a constraint on the pieces that you can put together to assemble to define an architecture. A great example of that is a layered architectural style, which basically takes the components of your application, organizes them into layers where each layer has very well-defined responsibilities, and then actually constrains the dependencies between those layers. Either you have strict layering so that one layer can only depend on the layer immediately below it, or you can have relaxed layering where it can depend on any of the layers below it. So that's an example of an architectural style. So then the question is, well, who cares about any of this, right? What's the point? Why should we care about architecture? And it turns out that if you look at the requirements for an application, they fall into two categories. You have the functional requirements, what it does, the use cases, and the stories. And that's sort of tied into domain knowledge. And you have the non-functional requirements. In general, you can satisfy the functional requirements of an application with any random architecture. It's not necessarily easy. And proof of this is the fact that a great many sort of key applications inside enterprises are just these big balls of mud, right? They have they might have had a good architecture once, and it's just sort of, they've decayed into squalid, sprawling slums of code. But they still manage to work, and people still manage to maintain them, albeit painfully and slowly. Not suggesting that any of you work on code that is a squalid, sprawling slum. That's actually a phrase from the big ball of mud pattern, which is worth reading. But then there's these non-functional requirements. And that's really where architecture matters. In order to satisfy your non-functional requirements or ilities or software qualities, you have to be very explicit in your architecture. If you go to Wikipedia or look at some software engineering book, you'll see a long list of software qualities or ilities. Obviously there's ones like, scalability, reliability, performance, though that's not an ility. Security, that's really important, especially if you work at Equifax, right? Or it is now. So there's a whole bunch that, and your choice of architecture dictates how well it dictates the ilities of your application. Well, the first three on this list are the ones that are particularly relevant today, or at least in the context of discussing the microservice architecture, namely maintainability, testability, and deployability, because those attributes directly impact your development velocity. If they're bad, you'll develop slowly. You'll deliver features slowly. If they're good, you will be able to deliver features quickly and make the business happy. So those, in a sense, it's those software quality attributes and your efforts to sort of achieve good kind of qualities there really dictate whether you're going to go with a monolithic or a microservice architecture for your application. And that's, today, right, this is sort of said quite often, businesses need to innovate faster. Super competitive market and all of that. And what that means for us as software developers, we build the platforms that enable the businesses to function, we need to build better software faster. And so architecture is becoming increasingly important. And sort of two key metrics here are reducing lead time, reducing the amount of time it takes from the developer committing a change to that change being pushed into production. And then another key metric is increasing deployment frequency, how often you're able to push changes into production. And we're all about kind of reducing lead time and increasing deployment frequency. And later on, I have a slide with some numbers on, sort of illustrating the state of the art. So if you think about, how we want to develop software today, it's really DevOps, and a huge part of DevOps is continuous delivery and continuous deployment. From an sort of organizational point of view, we want to have small autonomous teams. And then the other part of it is, we have to have the architecture that enables us to have that to practice DevOps and continuous delivery. And also we want an architecture that enables the teams to be autonomous. And that then leads into this whole discussion of a monolithic architecture versus a microservice architecture. So, imagine like you're working on an online store. You might have sort of a logical architecture that looks like this, where you will have layers, a presentation layer. You're going to have sort of data access layer and business logic tier layers have been sort of merged into one in this diagram. You're going to have various modules or packages representing different sort of chunks of business functionality. So a catalog module, recommendation module, review module, order module, and so on. So that's our logical view. And we all strive to build, three-tier modular applications that look roughly like this. But then, normally what we do, this is the traditional monolithic architecture, we just package everything up into a single component, a single executable or deployable unit. So in the Java world, that would just be a WAR file or an executable jar. So we've gone from this logically modular and layered system into just this monolithic system at sort of runtime, or actually kind of the result of the build is this one artifact. So, that kind of leads to the definition of what is the monolithic architecture. So it's an architectural style that structures an application as a single executable component. So there is a variation of this where you might have several executables, but they actually are tightly coupled through a shared database. So much so that they have to be deployed in locksteps, which makes them basically just one thing. I've encountered that. So, the monolithic architecture is not necessarily bad. If you have a small monolith, it's very likely to be very maintainable, easily tested, and easily deployed, right? You can quickly test it. You can easily write tests. You can easily understand it. You can easily run those tests and push it into production. So you can do your DevOps or continuous delivery or deployment thing and be happy. So that's quite good. The problem you have is that if you're successful, your application is likely to live for a very long time. And your application, which was once small, is likely to keep growing and growing and growing. And probably because you're successful, you're going to have more money. So your team's going to grow as well. So it's just this small application is just getting bigger and bigger and bigger. and the team that's developing it is getting bigger and bigger and bigger, which means that the rate of change is actually increasing as well. You're going to try and split into sub-teams, but you're really all contributing to this same code base. So those teams are trying to be autonomous, but they're not really. And eventually, you just end up with this massive application. At which point, any notion of sort of being agile or doing the DevOps thing becomes really impossible. And a lot of the other things happen, usually because the application is too large for any single developer to understand. Modularity breaks down, which ends up being kind of this death spiral to this big ball of mud, and that's sort of how you end up with this squalid, sprawling slum, where you try and make a change, and you don't quite understand how things work, and you introduce bugs, which delays the release, and no one's happy, right? You're basically in monolithic hell at this point. And I think there's a certain inevitability. In theory, you can try and preserve modularity, but I think at some point it really does break down. And then not only that, you tend to be locked into the technology choices that you made at the start of the project, because it's not practical to do a rewrite to upgrade to the latest and greatest technologies. Even with, say, the Spring framework, which is backwards compatible, I've encountered clients who are stuck using an old version of Spring because there's some dependency, like some version of Hibernate, that they've used everywhere, and it's too time-consuming to upgrade to the new version of Hibernate that the new version of Spring requires. So they're just stuck in the past. Even worse example is if you're stuck using EJBs, for example. I mean, you kind of find that every so often. So every aspect of your application is just unpleasant, difficult to understand, you can't deliver, and the technology stack is just really obsolete. So you're just basically in this very, very unhappy place. You have poor software quality attributes. So, of course, the solution, or a solution, right, is to embrace the microservice architecture. So that's an architectural style that structures the application as a set of loosely coupled services. And then those services are organized around business capabilities. So each service is performing a business function, like order management, delivery management, and so on. It's basically a form of modularity where your modules are services that have very well-defined, explicit sort of boundaries that cannot be violated because you can only go through their APIs. And that helps preserve modularity. So the idea of business capability is an important one. So if you think about what a business does, it has a set of capabilities that are sort of these things that kind of deliver value. And they're often organized around, each capability is organized around a particular kind of core business concept, like order, inventory, delivery, and so on. And you take those capabilities and you just map them into a corresponding set of services. So that's kind of the idea. Interestingly, this definition doesn't really talk about size, right? One of the drawbacks with the term microservice architecture is that it kind of emphasizes, size. That's the first thing you hear, in particular, micro, tiny. And then you get into debates about nanoservices versus mini services, which is some bizarro concept that Gartner are talking to their customers about in secret. From my perspective, what matters really is that a service implements some meaningful business functionality, and it should be developed by a small team, and it should enable that team to deliver software with a minimal lead time so a very short time from commit to deploy, with a very high deployment frequency. And so the service could be small, could be tiny, or it could be, largish, whatever that means. It could be 20,000 lines of code. So whatever kind of can fit in the collective heads of a small team of people and be developed and deployed, or developed, tested, and deployed easily. So, that kind of then leads to this kind of the title of the talk, No Such Thing as a Microservice. And really, I keep hearing these. There was a period of time where everyone was saying, well, could I use a microservice for this, right? And really for me, the term microservices is a linguistic shorthand for the microservice architecture, which is an application architecture. So you don't have a single microservice. You have your application has a microservice architecture that is a collection of services. It does not make sense to think of a microservice in sort of isolation. It's kind of like quarks, right? I guess they can't. You got to have at least two of them. Another version of the talk should be microservices are not a magic pixie dust, because people think they can just sprinkle them on their development teams and it will fix their problems. That's not true either. It will make things worse, probably. So if we were to go back to the online store and look at the microservice version of this, it would look something like this. So what were modules before now become self-contained standalone applications or services. Each one of those services has its own database, or to be more precise, its own private data. They might be sharing the same database server. You don't have to sort of buy 10x as many Oracle licenses. But private data is key. Services cannot communicate via the database. They can't share database tables because that means they're tightly coupled, which defeats one of the main goals of the microservice architecture. You might also functionally decompose your presentation tier as well, have web applications that implement specific functional areas like product browsing, maybe a web application specifically for the product details page, because that's such a critical piece of functionality. You'd also have an API gateway, which acts as a facade sitting in front of those services, exposing an API, like a REST API or some other API, to the outside world, to say JavaScript running in a browser or to a mobile device. You might also have some kind of inbound gateway for handling messages as well. So the thing to note about this is that it is way more complicated than that monolithic architecture on the first slide, right? There was just this one thing you'd scale out. This architecture, there's many things that need to be scaled out. It kind of hints at the downsides of the microservice architecture. But the important benefit of this is that the individual sort of software quality attributes, or the software quality attributes of the individual services will be good. They're much smaller, they're easy to maintain, they're easy to test, and they're easy to deploy. And that's the goal. So that means that a team of developers can deliver software, deliver their service very rapidly. And that's kind of the main goal of the microservice architecture, to enable the continuous delivery or deployment of large, complex applications. So you basically decompose that enables you to go quickly. So going back to this triangle diagram, right? So the process is continuous delivery and deployment, organization, small autonomous teams, and the architecture is the microservice architecture. It means that your architecture has the deployability and testability that's required for continuous delivery and deployment. It also means that the teams can be truly autonomous. So a team will own one or more microservices or services that they can develop, test, deploy, and scale independently of any other services and any other teams. So it enables them to be autonomous, which is sort of another key aspect of continuous delivery and continuous deployment. And then that kind of enables an organization, ideally, to be a kind of high-performing IT organization from a DevOps perspective. And there's like remarkable differences between low-performing organizations and high-performing organizations. So, low-performing organizations deploy into production once a month. High-performing organizations, many times a day. Likewise, the lead time for changes is, in a low-performing organization, is like a month or more, low-performing, less than an hour. Which is kind of awesome. So it's all about moving fast, but not only that, these high-performing organizations, according to the DevOps survey, manage to move fast and not break things. So it means that when they do a deployment, it's really, really reliable. And in the rare situation that there is a failure, there's a bad deploy, they can quickly roll back. So that's the other way of putting it. It's all about, moving fast and not breaking things, which is awesome. The other thing the microservice architecture lets you do is evolve your technology stack. You're no longer obligated to use the same technology stack throughout your application. When you're creating a new service, you can use a new technology stack. If you're making changes to a service, you can rewrite it to use a new technology stack, so you can incrementally upgrade your application. And then sort of last point to make, it lets you experiment. So for instance, you've heard that Golang is really cool, right? Because Google's using it. So you build a new service using Golang, and then you realize that it's really just a 1990s version of C with a garbage collector. And you want to use a high-level language like Java instead. That's not a disaster, right? You've spent a bit of time learning Golang, but it's not been you haven't spent 2 years building this Golang project and deciding you don't like it. You've just spent a month or two, for instance. And that's okay. You've learned something useful. You don't like Golang. There's so many things about Golang I just find bizarre, actually. So anyway, it lets you experiment. That's the key point. You can try fashionable things. And sometimes you find that they work for you, and that's good. But other times, if it doesn't work out, it's not a disaster. And you've learned something. I just don't know how you can have a language without exceptions. I'm sorry. Okay, so the microservice architecture is awesome, but at the same time, it's not. As Fred Brooks, the author of the Mythical Man Month said, there's no silver bullets. There are these no perfect technologies. And the microservice architecture has some fairly considerable downsides. And I think by far, it's complexity, right? If you were to sum it up into one word, there's a lot of complexity that comes with the microservice architecture. Development time complexity. You're building a distributed system, so you have to deal with inter-process communication. You have to deal with the fact that you might invoke some service and it might not be available, or worse, you might not get a connection refused. It might just be exhibiting ridiculously high latency. That's a huge problem. And then the fact that your data is now scattered across multiple databases creates just totally changes how you do transactions and querying. And we have this we just use ACID transactions and joins without really thinking about it in a traditional application. And both of those are problematic in a microservice architecture, at least if you're trying to span service boundaries. Testing is an interesting one because testing is simultaneously easier and harder. It's easier because the services are small and easier to test. The challenge comes from making sure that the services work together. Because what you don't want to do is some complex end-to-end test. But the good news is there's various testing strategies that you can employ, like consumer contract testing. It's just an extra wrinkle. And then from a deployment point of view, you no longer have a single application. You have potentially tens or hundreds of applications, each one of which will have multiple instances in production. That all need to be monitored and managed and coordinated, and so it's just there's just this extra complexity there. So you have to think: are microservices a good fit for my application? Is my organization mature enough to actually take on the microservice architecture? Are we good at automated testing? I think I looked up some survey last night, and it was there was only 26% of organizations do extensive automated testing. And there's a lot that do mostly manual testing. Microservice architecture really needs a high level of test automation, plus a whole bunch of other things, right? Requirements need to be broken down into small, independent chunks that can be delivered incrementally. Whereas if you've got that sort of legacy mindset of, massive requirements that take 6 months of development, it's questionable whether there's any value for using the microservices. Or if you have a centralized data group that want to define a global domain model, right? Which actually is very much at odds with DDD as well, so let alone microservices. That's an organizational impediment to using the microservice architecture. And you need to do something about them. Well, it came up in the workshop. Ignoring them was one. But it's like you have these organizational kind of structures that are an impediment, I think, to DDD and also to the microservice architecture, where you're really pushing responsibility down into the teams as opposed to having it centralized. So the good fit. Oh yeah, do I have the prerequisites? Talked about that. So the next thing is, and then if you do decide to use the microservice architecture, a whole ton of issues that you have to deal with. And so there's whether it's a good fit, it kind of depends. So to help with this, I created this microservice pattern language that's a collection of patterns for addressing these issues. So a pattern, of course, is a reusable solution to a problem that occurs in a particular context. Popularized by the Gang of Four book, which was object-oriented design patterns. But of course, patterns are much more general than that. DDD itself is a collection of patterns. And I think patterns are awesome because they encourage objectivity. So if you follow the pattern structure, it forces you to be much more objective about a particular sort of design approach or a particular technology. Because patterns have a name. They have to describe the context within which you're trying to solve the problem. They obviously have to describe the problem. You have to describe the issues that you're trying to address. You have to describe the solution, right? So you're trying to solve a problem in a context with such and such a solution. But then the most kind of critical part of a pattern is that you have to describe the resulting context. What are the consequences of applying this pattern? And that includes the benefits, the good stuff, which is normally what, when we're excited about a technology, what we focus on. But you also have to describe the drawbacks. What are the downsides? So like in the case of the microservice architecture, you have to, it's the fact that you're building a distributed system and there's a bunch of complexity there. And that actually, you also have to describe the issues that you must address. So it's sort of like you've applied this pattern, you've created a whole bunch of sub-problems for yourself at this point, which you must solve somehow. And then there's the related patterns section. So that actually describes the alternative solutions, which in the case of the microservice architecture would be the monolithic architecture. And then you also have to describe the solutions, then there are also the patterns that solve the issues that were introduced by applying this pattern. So it's like you apply the microservice architecture, that creates like 15 issues that you need to resolve. And then the pattern, the microservice architecture pattern, would actually say, well, you can use these other patterns to solve the issues that I'm creating for you. So these patterns end up forming this web, which is a pattern language. So this is the microservice architecture, which you pattern. And basically on the left, it's too small to read, but on the left there's the monolithic architecture and the microservice architecture. So those are the top level choices. And then everything on the right are patterns that solve the problems that are introduced by applying the microservice architecture. So if you go to microservices.io, you will find a readable and clickable version of this map due to some handy JavaScript library I found that can do image maps with unresponsive images. So I'm going to just kind of quickly step through this in the remaining time. So basically the idea with the pattern language just kind of guides you with, in terms of the decisions that you must make, and then for each decision, what the available options are and what their sort of respective benefits and drawbacks are. So if we look at the key patterns, right, so the first issue you have to decide is, what's my architecture? And there's a bunch of forces. And there, the high-level choice is between the monolithic architecture and the microservice architecture. And I should say that double-headed dashed line, that indicates that these two patterns are alternatives, approaches. So it's like single executable or a service-based architecture. Those are your choices. And then you decide, great, I'm going to use the microservice architecture. So then the next issue you have to deal with is, well, how do I decompose my system into a set of services? And there's a couple of patterns. You can decompose by business capability, which is kind of the main way. And in a sense, you can decompose by DDD subdomain. There's kind of this... It's funny, I haven't really mentioned DDD at all in this talk, but there's a lot of interplay between the microservice architecture and domain-driven design. You can view a service as a bounded context with its own domain model. Though interestingly, that is not necessarily like a linguistically driven bounded context in the true DDD sense of the word. So there might be kind of overloaded definitions of the term bounded context. So you come up with a decomposition. Another key issue is, how do you maintain data consistency in a microservice architecture? Because you might need to basically have the equivalent of a distributed transaction that spans multiple services. That came up in the kind of one of those long-running workflows that were described in this first session in this room. And the solution there is to use a saga pattern that is a sequence of local transactions that are basically strung together using messages or events. Kind of like this mini sort of workflow, but much lighter weight. And then there are various patterns that can be used to implement a saga such as event sourcing. Or alternatively, the application can simply publish domain events. Bunch of different options there. And then related to that, you also have to figure out how to do queries. You can't do distributed queries in the traditional sense across multiple services. And there's a couple of different patterns you can use for that. API composition, which is simply where if there's 5 services that own the data you need, you just ask those 5 services to give you the data. The alternative is to use CQRS, Command Query Responsibility Segregation, where you just maintain a separate view by subscribing to the domain events that are published whenever your data changes. API composition is simpler, but isn't always efficient, so you have to use CQRS. So those, to me, are the core patterns. Then there's a whole bunch of sort of technical stuff, which interestingly, a lot of people seem to focus on, like, oh, Docker, 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 right, is kind of almost synonymous with the term microservices. But they're much less interesting in this compared with the first few. So you have to deal with issues around inter-process communication, and there the choice is between messaging and REST or RPC, or maybe a domain-specific protocol as well. So, and interestingly, I mean, we've mostly focused on REST today, but I think you're going to see that messaging / events is going to probably be the predominant inter-process communication mechanism in a microservice architecture. You just use REST with the outside world. And even then, think protocols like Google RPC are actually perhaps superior. You might need to build your services on a framework, like a microservice chassis such as Spring Boot, Spring Cloud, or the equivalent in some other languages. And then, of course, there's the deployment issue. And there's a lot of options. I think probably the best ones today are to try and use a serverless deployment option like AWS Lambda if you can. Alternatively, use a Docker-based deployment infrastructure such as Kubernetes or Docker Swarm, or you can use VMs. And there are various trade-offs with each one of those options. And you also have to come up with a service discovery mechanism as well. Especially if you're running in a Docker environment, your service instances have dynamically allocated IP addresses. So if you want to make an HTTP request to one, you need to know its IP address. That's a remarkably hard problem in a modern application because of dynamic IPs. So you need to choose a mechanism. Like, for instance, Netflix Eureka is a very popular one today, though in many ways just using the discovery mechanism that's built into a deployment platform like Kubernetes or Docker Swarm is kind of simplifies your application. And then also you need monitoring. It's really important because requests come into your system, they bounce around, and it's like, how the heck do you troubleshoot it? So you need to put in place log aggregation, for instance, along with distributed tracing, health check mechanisms, and each service should have a health check endpoint, and so on. So these are sort of patterns that solve all these critical design issues. And behind each one, there's a lot of a certain amount of complexity in the sense of the discussion of the various trade-offs and issues associated with each one. So I'd encourage you to go check out microservices.io. So that's pretty much all I have to say, right? So in summary, right? So the goal of architecture is to satisfy sort of your non-functional requirements, and in particular, today, we need to choose our architecture carefully in order to be able to practice continuous delivery and continuous deployment. So if you've got a small application, the monolithic architecture will be just fine. It's not an anti-pattern. But for a large, complex application, you're probably going to end up using a microservice architecture. and you should use the pattern language to help guide your decision making. Both in terms of which architecture to pick, and then if you choose the microservice architecture, how to apply it effectively. So that's my talk. Hope you found it useful. Thank you for listening. And I should say, I guess we don't have any time for official questions, but it's sort of lunchtime, so I'm not going to pass out from hunger just yet.
Can I ask an unofficial question?
Oh, yeah.
So could you say a little bit about why there's an overloaded definition of bounded context in the microservice world?
Oh, yeah. So the question is, why is there an overloaded definition of bounded context in the microservice world? Well, so one definition of sort of what is a microservice, this came from like Adrian Cockcroft. I mean, he basically says it's a bounded context, right? And then, which on the surface sounds good, and I primarily agree with it in the sense that a service has an API, and behind that API, you're free to do modeling as you see fit, right? I would say. But in reality, the other goal of a microservice, I'll just use the term microservice, is to enable a small team to be super productive. So there's sort of a constraint on how large that service can be, right? Whereas if you then put on your DDD hat, then I think, bounded contexts tend to be driven by linguistic concerns, right? Where there's a term like order which has multiple meanings inside an organization, and so you kind of you have multiple models with multiple bounded contexts. And that set of bounded contexts might not be directly mapped to your sort of services, given that each service is claiming to be a bounded context as well. It's just a thought. Yeah. Oh, yeah. So the question is, sort of how do you go about testing microservices other than just consumer contract testing? Well, kind of a key idea behind microservice testing strategies is that you try and avoid doing end-to-end testing. Like there's this, whole concept of a testing pyramid where at the base, the wide base, there's lots of unit tests, and at the tip there's exploratory testing, and below that end-to-end testing. So in other words, you do very little end-to-end testing. And so the idea is, what does that mean in a context of a microservice architecture where an end-to-end test is really testing services together? And so the idea with consumer contract testing is if I'm working on a service and I'm consuming your service, I'm going to basically give you a test suite that you will run as part of your service's test suite that verifies that your service behaves in a way that my service expects. So that's one thing. So if you break those tests, you and I need to have a conversation. And then the other side of it is when I'm running a component test for my service, I'm going to use a mock for that other service so that I'm not having to launch it along with its transitive dependencies when I'm testing my service. So it's sort of like on one side you're using consumer contract tests, on the other, on the consumer side you're using mocks for the service you're consuming. And there are frameworks like Spring Cloud Contract and another one called Pact, where basically you have one definition of the interaction between the services that's used both for the consumer contract test and also for the mocking on the consumer side as well. And that to me is like a key testing strategy. So and so the whole goal is really to do this independent testing. And hopefully, if that works, you can just push it into production, you know. It's like there's a great cartoon where it's like, I don't always test, but when I do it in production, right? But that's basically, I think, like what a lot of companies doing, but it's not as casual as it sounds because they've very rigorously done all of this other testing anyway. And then when you do a deployment, you're probably going to do a canary deployment where you're going to roll out one new instance and monitor that very carefully and make sure it works before scaling out the version 2 of your service. And obviously, I mean, you look at internet companies, you know, they have incredibly good uptime, right? You know, like you can watch Netflix 24/7 and it just works, right? And likewise with Amazon, I mean, there was some statistic where Amazon are deploying into production every 11.4 seconds, right? They haven't, I don't remember an outage. And there's some statistic, it's like 0.0001% of their deployments have an outage or have a problem. Some crazy reliable statistic like that. So it's all about being disciplined and employing the right testing strategies. Any other questions? Well, I guess it's lunchtime. Thank you.